Hi, in this video we will see how to configure DE1 SoC both infrared module, both receiver and transmitter module. So we have the Verilog code for receiver and transmitter and to configure those. So and we also have the synopsis design constraints file where we have defined four clocks, each with 20 nanosecond period, which is 50 megahertz. So let's compile the design. The synthesis is done now. Let's look at the resource utilization. So if you see here, the total ALMs used is 183. The total flip-flops, that is registers used is 275. The total IOs is 241. And there are 0 block RAMs, DSP blocks, PLLs and DLLs used. So let's go to timing analyzer and we'll check the maximum frequency. So the maximum frequency is 160.57 megahertz, and let's also check the top five critical paths. Okay, these are the five most critical paths, and all these have a positive slack, which means the flip-flops in these paths are able to capture the correct values, and the delay is 5.952. Oh, this is the maximum delay. Okay. Now we'll look at the actual place and route of this critical path, and we'll try moving the flip-flops and the flip-flops in the critical path, and we'll see how it affects the delay. So let's open the chip planner, and if you look here, this is our critical path. So what we'll do is we'll move this to the X1, Y1, and we'll see how our maximum frequency and delay changes. Okay, now we have moved the lab combinational cell to the X1, Y1 coordinate. Now let us resynthesize it and we'll see how it has affected our delay. So let us close this and this as well. Let's synthesize this again. Now the synthesis is done. Now let's look at the timing analyzer. Okay, this is the maximum frequency. Now let us look at the slack. Okay, now the synthesis done. Let's look at the timing analyzer. Okay, if you look at the maximum frequency, it has reduced. The initially the maximum frequency was 160 megahertz. Now it has reduced to 83.35 megahertz because we have moved the cells, so the length of the wire has increased. That has increased our delay, hence the frequency has reduced. Regarding the timing, so if you see here, the slack also has reduced from 13 to 8, which means uh, there is only like 8 nanoseconds of extra time once the flip-flops captures the data. So the delay has gone up from 9 to 11. Okay. We will close this and we'll change the synopsis design constraints file. Let's make the clock to 2 nanoseconds and check how the critical path and the timing. save this and synthesis again. The synthesis is done now. Let's open the timing analyzer. The Fmax is 87.54 megahertz and the timing. So if we see here, if we reduce the clock period from 20 to 2, we are getting a negative slack, which indicates there is not enough time for the flip-flops to capture the data. Okay, so now we look at the batch file configuration. Okay, before seeing the batch file configuration, there is one way to overcome the negative slack, which is by including more flip-flops between the combinational logics. So that by doing that, we'll be able to overcome the negative slack. So now let's do the batch file configuration. So here we have the batch file and the SO file in the same folder. Now let's run the batch file. The board is already connected to the laptop. Yeah, now the board is configured through the batch file. Okay, now let's look at the board.
The board is now configured using the batch file. That's all. Thank you.